Namaste. Today we will do remaining questions from exercise 10.1. Before that, let us check what is the theorem 10.1. The theorem 10.1 states that the tangent at any point of a circle is perpendicular to the radius through the point of contact. That is, if this is a given circle and this is a tangent, that is, tangent passes through a single point on the circle and this will be the point of contact. Now this is the center of the circle and this will be the radius of the circle. Let us name this point as P and this line be X and Y. Now the theorem states that the tangent at any point of a circle is perpendicular to the radius. That is, on this point, here it will be perpendicular, means it forms 90-degree angles. Now coming to the third question in 10.1, a tangent PQ at a point P of a circle of radius 5 cm. That is, in a circle there is a point P which a tangent is passing through the circle and here the radius is 5 cm. Meets a line through the center O. That is, there will be a line passing through center O and it meets at the point Q. Here the tangent meets at the point Q. This is the tangent and there is a line passing through the center and both tangent and the line meets at the point Q. So that OQ is 12 cm. Here this OQ is 12 cm. You have to find out PQ length. So you can see a right triangle here. Here we know it is 90 degree according to theorem 10.1. Here it is 12, that is hypotenuse is 12, height is 5. You have to find out the base. So applying Pythagoras theorem, we know OQ square, that is hypotenuse square, is equal to base square plus height square. Here height square is OP square and base square is PQ square. So OQ square means 12 square is equal to 5 square plus PQ square. Now 12 square is 144. This 5 square taken to the other side, it becomes minus 5 square and 5 square you know 25 is equal to PQ square. 144 minus 25 is 119 is equal to PQ square. We need only PQ, not PQ square. So taking the square roots on both sides, here we will get PQ. So taking square roots, this becomes PQ and on this side if taking square root, it becomes square root of 119. So we have options here and option D is square root of 190. So we will choose that. Now coming to question number 4. Draw a circle and two lines parallel to a given line such that one is a tangent and the other is a secant to the circle. That is, here we have a circle. Let this be the center and you have to draw a tangent and a secant, but the condition is both must be parallel. So first we will draw a secant here. That is, in a secant there will be two intersecting points on the circle and tangent we have only a single intersecting point and here the condition was both must be parallel. So this secant and this tangent are parallel. Let us name these XY and let this be AB. Here XY is parallel to AB. Now let us check theorem 10.2. It states that the length of tangents drawn from an external point to a circle are equal. That is, in a circle, from an external point, we are drawing two tangents. Tangent means we will have one intersecting point. So from this point, we are drawing a tangent. And also from this point, we are drawing another tangent. So here, we have to prove that this length and this length are equal. That is the theorem 10.2. So let us name these. Let this be P and the center is O. Here we have Q and here we have R. To prove the theorem, we are going to join OP, OQ and OR. Now according to theorem 10.1, we know here it will be 90 degree. That is, from the radius, the point of contact of a tangent forms 90 degree. So this is a tangent, this is the point of contact, this is actually a radius. So here it will be 90 degree. Similarly, again this is another radius. Here this is a point of contact and here we will get 90 degree. So these two are right triangles. So we have to prove QP and PR are equal. So for that we will consider angle Q equal to angle R. Both are 90 degree. In right triangles, one is PQO and the other one is PRO. From these two triangles we got angle Q and angle R are equal. Next we can see PO is common for both the triangles. PO is common for this one and this triangle. And you can see if this is 90 degree, if this is a right triangle, this side is hypotenuse. In this below triangle, you can see this is right triangle and the side opposite to it will be hypotenuse. So PO equal to PO, they are common. Also, those PO are hypotenuse of right triangles. Now coming to OQ and OR, they are equal because they are radius of a single circle. So all the radius length will be equal. And those radius are actually right triangle's side. These are sides of this right triangle. Now, the congruency RHS, that is we have a right angle, we have hypotenuse are equal, we have sides are equal. According to RHS congruency, these two triangles, that is triangle PQO is congruent to triangle PRO. Now we can consider PQ from this triangle and PR from the other triangle. They will be equal. The reason is corresponding parts of congruent triangle, that is CPCT. So we proved PQ is equal to PR. Now coming to the circle, we can see both are the tangent lengths which is drawn from one single external point. So PQ equal to PR. That was the theorem.